Today's lecture is on ring theory, and we'll begin by revising the sheet that is dated 4th of March 2020. Now for the first question, you are supposed to give the definition of the following terms: an ideal and a principal ideal. So now we define ideals for ring. So we'll say that let R be a ring, and ideals are special subsets of ring. So we take a subset I of R. So then we say that I is an ideal of R, and the notation is this. That is if IR is equal to I is equal to I. So in other words, you have that whenever you take any element in R, so take an element, say A in R, then AI must be a subset of I, and similarly IA must be a subset of I. Now next, a principal ideal. So we'll say that whenever you have an I, so given an ideal I, so we'll say that I, for an ideal I of R, we say that I is principal, and that is if I is equal to AR for some A inside R. In other words, this ideal I is generated by a single element. So now next, you are supposed to show that the ring of polynomials with rational coefficients is Euclidean. So now these are the things that we're supposed to show. So we need to show clearly that this set, rather this ring, is a commutative integral domain. In other words, it commutes, and at the same time it has no zero divisors. Then number two, you also need to show that there is defined an integer valued function say gamma on elements of this ring satisfying the following. So number one, we want this integer valued function defined for any single element to be less or equal to this integer valued function defined for a product of two elements. Now in our case, this integer valued function is a degree function, and we know that the degree of a single polynomial is less or equal to the degree of the product of two polynomials, because the degree of the product of two polynomials is obtained by adding the degrees of the individual polynomials. Then what you finally need to show is the following: that whenever you're given say A and B, those are two polynomials, both non-zero, then we can define division by remainder. That is, you can say then there exist polynomials, or I'll just write Q and R still in this ring such that A can be expressed as QB plus R. So this Q stands for the quotient and R stands for the remainder, where the remainder is either 0 or this integer valued function, in this case the degree of our remainder, is still less than the degree of the divisor. And so finally, for this part of the question, you are supposed to find the generator of this ideal. So you have the ideal x squared minus 1 plus x squared plus 2x, sorry, this will be x cubed plus 2x squared plus 2x plus 1. So we know from previous lessons that the generator of this ideal is nothing but the GCD of the generators of the individual ideals. And so what's the GCD of x squared minus 1? So plus 2x squared plus 2x plus 1. So now to find the GCD, we'll make use of the division algorithm. So we'll first of all start by expressing x cubed plus 2x. So we start with the polynomial with the greater integer valued function, in this case with the higher degree. So that is x squared plus 2x squared plus 2x plus 1. And then you express it as some quotient times x squared minus 1 plus some remainder. And so if you work out this, you will get that the quotient is x plus 2, and the remainder is 3x plus 3. And of course, you get this by just doing the usual long division with polynomials. So next we are going to take this second generator, the generator of the second ideal, and then we want to express it as some quotient times 3x plus 3 plus some remainder. And again, if you work out this, you'll find that the quotient is 1/3 of x and the remainder is minus x minus 1. So next we are going to express this polynomial as some quotient times this plus some remainder. And if you look at this keenly, we simply need to put minus 3 here and the remainder is 0. So using this algorithm to find the GCD, usually the GCD is the last non-zero remainder, and the last non-zero remainder is at this level of calculations, and so the GCD is minus x minus 1. And so we can take the generator of this ideal to be the element x plus 1. Okay, so the second question, express 198 as a product of prime factors. So 198 equals to 2 times 99, and this is 2 times 9 times 11, which is 2 times 3 squared times 11. And then for the second part of the equation, hence explain whether 198 is expressible as a sum of squares. So now there's a theorem in number theory that a number is expressible as a sum of squares if all the prime factors occurring in its prime factorization, which are of the form 4m plus 3, occur in even powers. So as you can see, the only two prime factors which we are now going to look at are these two, because 3 leaves a remainder of 3 when divided by 4, and so is 11. And so 3 occurs to a power of 2, 11 occurs to a power of 1, so 11 does not occur to an even power, and so this number is not expressible as a sum of squares. Okay, so next, find all the elements of this finite field. So while studying about finite fields, we said that suppose you have this quotient field where this is an irreducible polynomial of degree n, then the number of elements in this field equals to p to the n. And so that means that here the number of elements that we'll have for this finite field is 2 squared, which is equal to 4. And now how do you get those elements? The elements are obtained by looking out for the remainders when you divide any arbitrary polynomial over z2 by x squared plus x plus 1. And so the possible remainders here will be 0, that is if the two polynomial, I mean if this polynomial divide into that exactly, then we can also have a remainder of 1. We can also have a remainder of x and a remainder of x plus 1. And so these are the elements in that finite field. Okay, next we have some 2 elements in the ring of Gaussian integers. And now we are required to find the quotient and remainder when the 2 elements are divided. So when you want to find the quotient and remainder when you divide these 2 elements, then you can just apply our knowledge from complex analysis, just do the division, but then we ensure that what we have at the end of the day are elements in the ring of Gaussian integers. Of course, when you are dividing the field of complex numbers, then we don't have quotients and remainders because everything divides exactly. And so in order to carry out this division, we need to multiply both the numerator and denominator by the conjugate of the denominator. And so the denominator gives 1 squared plus 3 squared. That one, know that is the square of the real part plus the square of the imaginary part. And then for the numerator, we'll have minus 3 minus 2i minus 9i, then we have minus 6i squared. And of course, this is nothing but, we know that I squared is equal to minus 1. So this will give us plus 6. So what we have here is minus 3 plus 6, which gives us positive 3, minus 2 minus 9i gives us minus 11i, and all this over 10. So assuming that we were in the field of complex numbers, then this could have been 0.3 minus 1.1i. So now when we get to this level, we simply need to look for the Gaussian integer which is close to this. And so we know that 0, as you can guess that 0 is closer, or is the integer which is closest to 0.3 than any other integer. So we take this to be 0. And then the integer which is closest to negative 1.1 could be 1. And so our quotient is I. So we can say that 3 plus 2i is negative I into minus 1 plus 3i. And so let's look for the remainder. So if you multiply minus I by minus 1 plus 3i, we'll get 3 plus I. So as you can see, the remainder will be 3 plus 2i minus 3 plus I, and that is I. So now we have the quotient is equal to minus I, and the remainder is equal to I. Okay, fine. So for the last question that we're going to look at under this problem sheet is the following: that suppose you are given a ring with unity, and suppose you have two elements, say A and B, in that ring, with AB equals to 1 and BA not equal to 1, and as you can see this is not a commutative ring, then we're required to first of all prove that 1 minus BA is idempotent, and also to show that 1 minus BA composed with B is equal to 0. And so to prove that 1 minus BA is idempotent, we need to show that 1 minus BA, so that when we compose this with itself, we get the same thing, that is 1 minus BA. So when you compose 1 minus BA with itself, you get 1 minus BA, 1 minus BA. And if we carry out the usual algebraic products, we'll get 1 minus BA minus BA plus BA, BA. And then we recognize that AB is equal to 1, so this is 1 minus BA minus BA plus B times 1 times A, and this is just BA, so that eventually when you take 1 minus B, eventually when you take 1 minus BA plus BA, we get 0, so this is 1 minus BA plus 0, which is 1 plus 1 minus BA. And so now for the second part, we show that 1 minus BA times B is 0. So 1 minus BA, when you compose with B, we get B minus B AB. But now, what now we get to recall here is the fact that AB is 1 under the composition law, so this B minus B times 1, which is B, and then B minus B is 0. So that marks the end of the problem sheet that we are out to revise for today. So have a lovely time revising.